workshop, a triple workshop on metrology for lighting environment. Thank you especially to participate to this first day, that is the tutorial day. It is a tradition in this kind of workshop. And thank you to the speaker of this day, that are Professor Stefano Loreti and Professor Lucia Figuli. Thank you to be here, and thank you to share with us your specific expertise. Sorry for the delay. But however, we are in the academic delay. It is a tradition also, particularly in Italian tradition. So thank you again to be here. And let me start this day giving the floor to Stefano Loreti. And the title of his speech is Passive and Active Infrared Thermography, Live Comparison of Cutting-Edge Excitation Strategies and Post-Processing for Investigating Masonry Materials and Wood Samples. Stefano, the floor is yours.
Okay, yes, sorry for the long title. And yeah, so if we can start the presentation, okay. Just a second. Okay, get it. Sorry, another delay. Anyway, thank you for being here. This is actually, and thank you for the opportunity given me by the organizer. As said, I'm Stefano Laureti. I'm a researcher here at the Università of Calabria at the Department of Informatic, Electronic Modeling and System Engineering. I'm in the group of electrical engineering, elettrotecnica for the Italian. It's a big group. It's only me and my boss. But anyway, today we will talk about a very hot topic, which is thermography. And in particular, I will give you some insight on what are the problems of the thermographic inspection, both passive and active. Of course, it cannot be exhaustive because it's impossible to do it in 40 minutes. But for me, the most important part of what I understood so far is that if you want to do something novel, you have to get some good solid base on the fundamentals of the topic you want to deepen. So anyway, let's start. Can I ask to reduce the icon of the Teams, if it's possible, because I have some videos. Okay, so I'll go on. So this is the outline of this tutorial. Basically, we will start with an introduction to infrared thermography, which we call IRT, just to save some time. We start with principles. So principle about how the heat diffuses in the sample under test, and what are the problems and issues that we get when we try to investigate such structure. We will talk about the excitation strategies. There are a lot of excitation strategies and exciting signal that one can design and send to the halogen lamp and excite then the sample under test. And basically, based on these different types of excitation, one can infer different information. And there are a lot of post-processing that have been developed with the time to deal with this kind of excitation. And so we'll have a look at some of them, not all of them. It's impossible now. Also with the growing of the application of machine learning, it's like skyrocketing, so it's impossible. The samples that we will inspect, we'll try also to do some live inspection. Of course, I saved the data, so just in case something will go wrong. Will be a green ceramic tile, which for us will be mimicking a wall masonry structure, and that is that one over there. it's already ready for be tested, and a wood inlay with some artificial defects embedded at different depth inside the sample. So the active IRT scheme that we will look at will be the step heating, which is quite the most simple. The long pulse, just a small difference, but in literature they stress these things a lot. And we'll talk about single frequency excitation and then lock-in processing. And also we will have a small look about the specialty of the house, is the pulse compression thermography. So the excitation is a sort of pseudo noise. It's a pseudo noise signal, and we have some peculiar properties that we can exploit at the end to retrieve some information. Then we will have a look on basic post-processing, which will be amplitude and phase imaging belonging to the lock-in excitation and scheme. Then we will have a look on image fusion, thermal signal reconstruction, which is widely used worldwide, and a brief look at the principal component analysis. Then at the end, I will give you some take-home messages. So let's start with the introduction. As said, I try to be effective but easy to be understood. So human eyes are sensitive to a limited range of electromagnetic radiation, which is the visible, of course. But as Neil Young say in one of his songs, there is more to the picture than meets the eye, of course. And this other part of the radiation is the infrared, which we will be exploited here. Usually in the literature, this infrared spectrum is divided into smaller ranges. And so we have the shortwave infrared, which goes from 0.7 micrometer till 2 micrometers. Of course, these are very raw numbers, so it can be a little bit, I would say, not so strict. The mid-wave infrared, which go to 2 micrometer to 6 micrometers, and the long-wave infrared, which goes from 6 micrometer to 15 micrometers. And this camera over here works on this range, so in the far infrared or long-wave infrared. So what we can see with exploiting something that goes beyond the visible. Here there are some examples, mostly based on frescoes and other cultural heritage stuff. But the last column is something that is very similar to what we have there, because it's a painted surface, but in the behind of it there is a wall actually. So we can see some underdrawings, of course, depending on the wavelength. This is mostly in the near infrared. Some signatures just beyond the book, the first page, the book cover, yes, and some pentimenti, what we call pentimenti. So it's basically something that the painters try to paint at the beginning, and then they say, okay, it's not what I wanted, but the preparatory drawing is still there, and it's kind of amazing. And past the restoration and detachments, which of course are similar to what we embedded inside there. So we have some voids, cracks, and we will also put some water in to mimic an ingress of water. So principles. The main principle is that every bodies radiate an electromagnetic magnetic radiation when they are at the temperature beyond 0 Kelvin. And of course, some, for example, the sun, it's at very hot temperature, so it radiates, it spreads the radiation in all the wavelength, and mostly, likely we have a peak in the visible, so our eyes sort of made a trade-off during the evolution, and so we caught that visible to see the things. And the other principle are that this emission is regulated both in the wavelength and in the peak of this radiation by some law, which are the Planck's law and the Stefan Boltzmann law. So to be more precise, according to the Planck law, the body emission at the temperature T spread the different values of the wavelength lambda. And according to the Wien's law, we have that the maximum of the emission shift towards the lower values of the wavelength lambda when the temperature increases. What it means, just have in your mind a very hot metal, and you make it very hot, you leave it in a room, you turn off the light, and you can see it, because it spread the radiation also invisible. If it's at the room temperature, you won't see it. Okay. So depending on this and this range of temperature, the engineers and the physicists, of course, design the thermal camera. So instrument that can catch this radiation and translate it to a voltage signal pixel by pixel. And why we don't have cameras in every range of the infrared? Because also we have to take into account the atmosphere. The atmosphere absorbs radiation, and those are the peaks of the absorption. So, for example, in the short wave, there is not a big absorption. Also, in the long wave, there is not a big absorption. So, if I'm smart enough, I will design a sensor that will work in the short wave, long wave. There are also in the mid wave infrared, but those cameras are expensive and cooled. So depending on the range of temperature, the engineers, as I said, design these cameras, and the scientists design these cameras. So the sun will spread the energy all over, while a body at the environmental temperature, it's around 300 Kelvin, will have a peak in the long wave infrared. So it's for this reason that thermal cameras like that are used a lot for bodies around the environmental temperature. So like in this case. So everybody knows a thermal camera, and to make a test, you just need a thermal camera and some patience. But anyway, the design of the excitation, how you made the measurement plays a big role on what you see and what you can infer from the thermal camera measurement. Also, because even if we are looking at an object which is at equilibrium condition, so I mean at the same temperature of the environment, we can get some difference. And we can see some difference. Why? We will see later, but the emission at each location, let's say a pixel of the image, depends on the emissivity, which is a parameter that takes into account the difference between a black body and a real body, which is gray. And so it depends on firstly, on the surface finishment of our bodies, and different surface finishing leads to a really high variation of emissivity. And emissivity is also a function of temperature. But for our cases, we don't have a very big variation of temperature when we run the test. So we neglect this variation. Anyway, there are people looking, for example, at furnaces, and they start with let's say, temperature of around 300 Kelvin, 500 Kelvin, and then they go up to 1,000 in hours and days. And so they have to take into account and correct the measurement, considering also the emissivity of the body that changes with the temperature. So some just a showcase, let's say, of application that we can have related to the living environment. These are just some examples of passive thermographic tests. There you can see the structure of a building, and you can also see if everything works well. So, for example, if you have leakages, or if you have uneven absorption, or temperature bridges or other stuff in homogeneities. For example, the picture, sorry, where is the, oh yeah, the picture, sorry, yeah. The picture here show a hidden window, which was then walled and bricks were placed into places, but you cannot see from the outside because there is the plaster. So it's hidden beneath. And this is a passive thermography. So we are just looking at the building straight away like this with using the thermocamera. That is an image that we made in a church that was undergoing restoration. And so you can see also the masonry structure of the wall behind the painting. And this is a great help for the restorers working in this field. So other things, so you can, for example, see some hot water leakages behind the ceiling, at the floor, sorry. You can see if something is wrong in some window, for example, a hot spot or something similar. Here there is a corner of a staircase, and this is like a very delicate point for the people working in the energy savings. And here is just a picture of a photovoltaic panel, and this hot spot means that the cell over there is not working properly. So it's emitting electromagnetic radiation due to Joule effect with some kind of leakage of current and overheating. Other stuff is that there are nowadays a lot of cameras that can be mounted on the drones, also unmanned aerial vehicles, and so you can have a very big look at a glance on a field of photovoltaic panels. Of course, you need to correct by the angles and by many factors. So this is not a difference only in temperature. It's just there are a lot of things to be corrected here to extract some features of interest. But this gives you an insight on what is going on nowadays. This is something that I like. Thermography is applied also in agriculture and food, not only for control, but also for trying to get the wisdom of wise men working, for example, in Japan, planting rice. So these old guys and ladies are, these old men and ladies are working in a rice field, and they how to say, forecast the amount of water that the rice needs based on some heuristic fact that they got it during their time working. And so these people are not being replaced by newer, younger generation. And so since the production of the rice can be stopped and needs to keep going on, there are people looking at trying to extract in some future from thermography that can give an automatic way to give some amount of water, temperature at which should be exposed. So trying to catch the wisdom of these guys. And also here, it's a big field. Basically, it's a ground planted with some oat or other stuff. And you can check the amount of water. For example, are these red and green differences that you can see. For example, here, the water content that went to the ground, it's quite similar. Here, instead, you need to give some more water to the ground to have an even water content overall, so to maximize the production. Now we go also to another part of the living environment, because thermography is also applied for looking at what is happening to us in terms of health, and also to the animals. For example, here there is a horse, and this one it's a sign of inflammation. So it got injured, and you can get also some information about the extension of the injury from the thermographic data. Here is something, of course, very careful and dangerous, but nowadays thermal camera, in some extent, they are also used to evaluate the state of possible cancer. And this is a very interesting fact, not only because of the importance of this, but also because it's not a direct passive thermography. They use an effect that we get, a feedback that we get from the body that will change the temperature when we touch something which is colder than our temperature. So if we touch something colder than our temperature, our body temperature increases. So you can see better the differences and infer some more information. It's kind of active, but there is a lot to do because there are a lot of false positive and a lot of false negative. So there is a lot to be improved. So let's go from passive to active thermography. For example, here I designed, I drew a sketch of a simplified stratigraphy of a wall. And there is, in a very simplified way, there is a plaster which covers the wall support. And we get an IR camera, which of course should be at the same side of the excitation or in the exterior or interior of the building itself. And we got an area of interest to which we are interested to extract information about possible detachment, inclusion, and other stuff. So how we get this information from that area, and now we know that we are really going to excite that area with our heat. So this is this slide show a bit of mathematics, and I used to demonstrate this a thermal stimulus in the form of a cosine. Why in the form of a cosine or a sine wave? Because, for example, the heat temperature, the sun temperature measured during the days, it goes like a cycle of 12 hours. Okay, and there are many active excitation that anyway it can be solved for any particular excitation because Fourier theory allow us to do it. So this is the temperature of simulated, of course, temperature of the surface of an object at different times. So it goes up and down, up and down. This is of course, is the difference in temperature. Okay. So I put just +4, -4, +4, -4. The heat propagates, diffuse is the real word, into the structure following this diffusion equation, which is a partial differential equation of the second order. And we got here this coefficient, alpha. Alpha is property of the body. So it depends on the conductivity, the density, and the specific heat of the body. Okay. So for example, that sample over there has an alpha, and the alpha coefficient is not the same for each pixel, for each X and Y division of our space, of our sample, and is not the same, unfortunately, if it's not isotropic, homogeneous and isotropic, is not the same also at different depths. So it changes. You take into account as it is constant, but it's not, even for a single body. So that coefficient depends upon the materials. If we solve this equation, we get to this. Okay, and this equation, even though it's a diffusive phenomena, it's the solution of a thermal wave. Okay, so we can look at this phenomenon as it is a wave that diffuses inside and have a sort of wavelength, okay? And this wavelength is the thermal diffusion length here, which depends on the frequency, angular frequency, so 2 pi f, and depends also on the materials. So if we change the materials or we change the frequency, this thermal diffusion length changes accordingly. What does it mean in simple words? So there we have the same graph as we had before. Temperature at the beginning, at the surface of the sample. Then we go into the sample and we look at like we have a different thermometer at different depth of the materials. And we see what is going on in terms of temperature at different wavelength. So here I just put an example, but the solution of this equation is this. So while the temperature changes very rapidly inside, the diffusing wave is something very slow and very attenuating. It's an exponential decay that decay exponentially with both frequency and depth inside the sample. These are millimeters, just because we need it afterwards. So, okay, let's say that the depth of the plaster, the thickness of the plaster is 4 millimeters, and we are interested in exciting with the heat something that is beyond 4 millimeters, okay? So here I put the diffusion coefficient alpha of that sample over there. If we excite with 1 Hertz, so 1 cycle per second of a thermal wave, what happens, what depth we reach inside is the depth of the thermal diffusion length, okay? It's a 1 over E amplitude exponential decay of the amplitude. So the thermal wave for that materials at a frequency of 1 Hertz, it's 0.4 millimeters. So if we excite with a single frequency, we get till 0.4 millimeter. So single tone, single frequency. So we want to go beyond. What we should do? We cannot change the sample, of course. We change the frequency. Here I go at 0.1 Hertz. So 1 cycle in 10 seconds, okay? And what we get is a very low diffusing and very slow diffusing phenomena, but I can reach a deeper depth inside the sample, okay? So I can go till here. Oh, sorry. I can go till here. So again, I decrease the frequency of a factor of 10, so 1 cycle in 100 seconds, and this should make think about the length of the test that we should carry out to reach that depth. So to reach these 4 millimeters, this purple line over here, we need a frequency of excitation, a very low frequency of excitation, which is 0.01 Hertz, okay? So 10 millihertz. With 10 millihertz, we are sure, mostly sure, that we can reach the depth of interest. So how we link these trends all over to make the active thermography? Okay, so if we look at the passive IRT, when we have a camera and a cycle in temperature which is 12 hours, it's like we have a very low frequency. And very low frequency, like, for example, omega equal to 0, angular frequency equal to 0, but it's very low, not 0, of course, means that the sensitivity of your measurement is the whole depth. But the problem is that that camera doesn't give you the temperature of each depth inside, does not discriminate. It's an integral measurement. So what you get is the response of the whole thickness, and it's difficult to get back the information. Instead, what you can do with the active thermography is once you have found a not spot in the sense of a sensitive spot that you have future of interest or some detachment or etc., you can modulate this heating source, not using the sun, of course, but using the halogen lamps or LED or whatever, and tailoring your excitation frequency to get to and over different depths. Okay? In a way, it will be an integral measurement, but at least you can somehow reconstruct what is going on inside, making a time analysis or a frequency analysis, and etc. So active thermography, how it works. You have some lamps. You can have the IR camera, infrared camera, at the same side of the illuminating system as here. We call it reflection mode, or on the other side, which is the transmission mode. And you record a matrix of pixels, which is the CCD of the camera, of the bolometer, or whatever. And you record it for a series of time instants. So you get a video. Okay? It's like a video camera, but looking at the thermal radiation. If we are in this situation, like we are here, and if we have a detachment from the plaster to the wall, what we see in this side of the CCD area is an abnormal variation of the temperature. So you see a higher temperature on your side of the camera. Of course, if the thermal excitation would be on the other side, then you will see a lower one. Anyway, in general, the active thermography has a goal. If we translate it to the circuit theory, we can say that we have an input signal, we have a system under test, each pixel of the covered from the camera of the sample there, and which signal we should use then to extract this information and to maximize the signal to noise ratio and the number of information that we can extract. So, I mean, the different depth of the sample. The most simple and known signal is a delta of Dirac. So it's a very short impulse. And for definition, if we look at each pixel of the acquired thermograms, what we get when we illuminate this sample, for example, with a single flash, high power single flash, we get the impulse response of the sample. And what is the impulse response of the sample? By definition, you have completely characterized the sample itself, okay? Because the FFT of the delta of Dirac, it's just a flat and constant amplitude in frequency. So you excite each frequency with overall the same amount of energy, okay? So the pulsed excitation, we cannot do it here. We have a way to do it, but I will show you tomorrow. And in the other talk I will give. But the pulsed excitation call for a setup which is, first of all, expensive, very expensive. And secondly, is harmful. So you cannot look at these lamps because they are very, very energetic in the order of 10 kilojoule or whatever. So you can really get blind. So better not to do it. This is called pulse thermography. It's the most used worldwide, but it requires some things. And it's very flexible, as I said, because with a single shot, you get the impulse response, and then you can do a time analysis, a frequency analysis. So you can discriminate different depths depending on the thermal wavelength. But if you get the FFT of the recorded signal, then you can discriminate. However, the signal to noise ratio that you can get is limited by the source power of your real illuminating system. You cannot go over, you have to add some lights and etc. So how you can instead maximize not the number of information or the depth that you span, but maximize the signal to noise ratio at a single specific depth. You use, as we said before, use a single frequency, okay? If you use a single frequency, then you maximize the signal-to-noise ratio at a given specific thermal wavelength. And this is what we call lock-in thermography. Lock-in, it takes the name not only from the single sinusoidal, the single tone, but also from the post-processing that we will make after, and we will look at in a few minutes. Anyway, this provides the highest signal-to-noise ratio, but of course you have low info because you have the info at a certain wavelength. Okay, so to span all the frequency of interest, you have to replicate and repeat your experiment at other frequencies, go over the whole range of interest. There are ways to do it, but we are also working on that, to do it at a glance, but it's quite difficult. Another common strategy that we will see here, and then I will start making you look at this, is the step heating. Step heating means it's very simple. You just illuminate the sample for some seconds, and then the temperature rises up, and when the heat meets some discontinuities, it will be reflected back or absorbed if there is water, depending on the specific local properties inside the sample, thermal properties. However, also it should be noted that the Heaviside step function, if you make the derivative of the Heaviside step function, you get back the impulse response, the delta function. But this is very noisy, you know. It's a square wave, so you can go up to infinite depending on the noise. There is a way to do it, but and we will see it later, but it's not that straightforward. We need something else to get rid of the noise. Then in the literature, you find also the long pulse thermography. So here, you don't stop your acquired signal, your acquisition at a time equal to this step. You go over, and you also collect the information from the cooling trend of the sample. And this gives you some further insight on what is going on inside. Of course, you know that if this is a square wave, for example, you have odd harmonics going on, so you are exciting a lot of different wavelengths. And you can then tailor your duration of the T-step depending on what you want to span inside. And this is a brief overview of this. So basically, the F0 that you are exciting, but this is, again, not a single frequency. You are exciting a number of frequencies in this range. The higher is the duration of the step, the higher is the first zero, the lower is the first zero of your frequency domain. So if you want to go deepen and get rid of the surface information, you just elong your time step. Otherwise, if you are interested in the surface, then you make it higher in terms of frequency, so narrower in terms of time duration, and you can enter some information. So we just run a test over here, because then I show you some acquisition. So here what we have is a non-made setup. There is a power generator that we control via LabVIEW. So we can, and this is an arbitrary waveform generator. And so we can excite that system of halogen lamps with whatever excitation we want, okay? And basically, it works like this. So for example, I want to excite with a step heating of, for example, 50 seconds. Depending on the material properties, of course. And we got something like this. Just wait a second. I don't know if you can see the screen, but it's very difficult to work with different things. So here is an example of a passive thermography test. Now it's the body is at environmental temperature. It's in equilibrium with the room temperature. So, and what we see are these spots over here. You can see my hand. These spots over here that are just emissivity variation on the surface. There are, we will see now, defects embedded inside. But let's say we want to run a basic, very basic step heating acquisition and step heating scheme. So what we do, just wait, because it's not instantaneous. I just run that and then I show you the example in not in real time. So it's just illuminating. The energy is spread toward the sample. The sample absorbs the photon, and then it gets hot. Okay, and since the properties of that materials are different at each location, we will see now a detailed scheme of the sample itself. We can infer some information on what is inside. So anyway, while it's running, we'll go. Francesco, sorry, how many minutes I have left? 10 minutes? Okay. So this is pulse compression thermography. We use coded signal, but we will see it tomorrow because it's a page not found. It's we will look at tomorrow. So that is the green ceramic tile that we have. And there are these defects inside, okay? There is a sponge that we can fill with water to mimic an ingress of water. So you will see it as a lower temperature compared to the other part. There is a piece of plastic that can be fallen inside by some mistakes. And there is also a wood piece over here. And so our aim is to identify this defect. The second sample that we have is this. It's a wood inlay and can mimic, of course, the things that you can have in a church or whatever. And it has different wood pieces inside, the nails and etc. But of course, it's not visible. It's inside and buried at different depths. I won't run the test again because there is no time. So results. I played the step heating. This is what you get. So we start from 0 and we follow the temperature rise in 2 pixels. One is placed onto an area on the plastic, where is the plastic, and the other one is related to a sound pixel area, so where there is no defect. What we are exciting is something with a t-step of 120 second length in time duration. So the first 0 in the frequency spectrum is 5 millihertz. So we are exciting, spanning all this diffusion length. So we are going beyond the thickness, not the thickness, but the area of the thickness of interest where our defects are, and also going till the shallower one. So the temperature rise is something like this. So while time elapses, you will see some differences. So here is the piece of plastic. Here is now, you can see the wood piece, because the temperature rise of this pixel and this other pixel, the sound one, are different, just this, okay? But you can see that even if I play around a bit with stars, there is a lot of noise, okay? The long pulse is quite the same, but you also look at what's happening in the cooling stage, okay? So probably I should play it a bit fast forward, but let's wait for it. At a certain time, which is equal to 120 seconds, the temperature will fall down and following an exponential decay like this. So also information can be extracted from this part and from this part, okay, in 2 separate ways. If you take into account the first part is step heating, if you take into account both sides is long pulse. There is a patented method from Professor Shepard, which is called thermal signals reconstruction, and say that since the decay is exponential with the time, so if you plot the logarithmic of your time, which is the acquisition time, and the logarithmic of the temperature difference from when you start the test to each point of your time. This should follow a straight line. Of course, it doesn't follow a straight line, but it's mostly a straight line. So what you do is you play with the number of this coefficient to make a non-linear fitting, and the number of this coefficient, it can range from 4 to 5 to avoid a lot of ringings or to be too much, not to be too much optimistic about your line. But there are a lot of studies on this. But what happened is that the real interesting part is that if you do the derivative of this, the first derivative and the second derivative, you can enhance the signal-to-noise ratio, and you can also infer other information such as the depth where the defects are located. And this is very easy to do. Once you obtain the coefficient, the derivation, second one and the first one are very easy. So this is the raw data. This is the thermal signal reconstruction, the first derivative of this and the second derivative of this. See here, you will see the sponge, which will appear at lower temperature because there was water inside, which is not really visible on the raw data. Neither, sorry, here it will be visible and here. Neither in the raw data. So see, and of course the signal-to-noise ratio is highly enhanced with respect to this. Okay, so I can play it again. It's very. Here you have really all the defects visible. Okay. So lock-in. What does it mean? Single frequency. I chose a frequency of 5 millihertz to excite it. And so the temperature rise will be something that goes with the period of your cosinusoid or sinusoidal signal. Goes up and down, up and down. So heating and decreasing temperature, heating and decreasing temperature. But of course, you can see that the signal-to-noise ratio is not quite high. Okay. So what you do is you apply a lock-in, like a lock-in amplifier. You take the reference waveform is the signal that you sent. You multiply it point by point in time for each pixel, and also you have another reference which is shifted by 90 degrees, which is the sine. And then you pass from Cartesian to polar coordinates, and you take this as an in-phase and a quadrature signal, and you can make it an absolute value and represent it, which is called R, or you can represent the phase. Okay, that's just an imaginary part over the real part. So what you get is an enhanced signal-to-noise ratio. I played around, and also you can fuse these images in a way you want, also using some image fusion. But you have always to have in mind the physics underlying. So you're trying to use the phase at sort of at the denominator to increase the signal-to-noise ratio or multiply it, etc. You can do whatever you want, but I think the best thing is to have the physics in mind. So these are the results from, I almost finished, wood inlay with a lock-in. Okay, so you can see that there are these two different wood pieces over here in the form of like a butterfly. Here is completely different, this circle here. Here there is like gypsum ticked inside. So, but of course you lose resolution because it's a single frequency, so you don't know. You can infer, but you have a single image. So what you can do is the last thing that I show you is to apply a sort of space reduction. It's a space reduction actually technique, which is called principal component analysis. So you say that an image can be reconstructed with lower, with a combination of different vector, basis vector, which depending on the application can be obtained by singular value decomposition, and then by looking at also the covariance of the matrix. So what you get is something like this. I just reduce it from 2000 time acquisition to 8. And you can see that the first one, the second one, up to the 7th one gives you some information what is inside, and you can also discriminate about the different defects better than the single image. But after the 8th one is just unuseful signals, just noise. But anyway, it's a space reduction, so it cannot be reconstructed a posteriori. But if you do the PCA all over and you have the same number, you don't reduce the space, then you can come back to the dimension of the space. Anyway, that's the end. So some take-home messages. Thermography is a very powerful tool when used with the due care. And you have to... It's me?
It's me? Yes.
I don't know what's happening. Okay. So the choice and design of the excited waveform must be tailored for a given inspection setup. There are a plethora of post-processing techniques available to enhance the defect detection. However, this should be applied with the due care. So you always have to have in mind what are you doing, and not just taking the best image and not saying everything till the deep of the physics. So see you tomorrow also for more insight on the coded signal, and this is the specialty of the house. So thanks for your attention. Enjoy the conference and have some hot nduja, because it's very good. I hope you like it. And last thing, myself, Professor Sara Casaccia is there, and Michael Svantren from Czech Republic. We are also, we made this special issue in MDPI buildings, so any submission is welcome. Thank you all for your attention. If you have any question, I'm here.
Thank you, Stefano, for your very interesting presentation. So before asking the attendees if they have questions, I would like also after the welcome by Professor Francesco, I would like to welcome you in this first edition of Metro event, and hoping that, but I already see that it is already a success. And so I am now asking you if there are some questions regarding this presentation. Yes, thank you.
Mm-hmm. Yes, we heuristically we have two cameras, one in the long wave infrared and one in the mid wave infrared. And we use it for frescoes analysis and also paintings. What we see is that cooling down the camera itself and the mid wave infrared it's much better. So the very expensive one that have a cooled polometer or cooled array of things, even if they work in another range, but the mid-wave infrared, it's, as you know, is a temperature range that does not exist from the point of environmental noise. Here you get all the noise. Okay.
Any other question?
Yes. Yes, we experience it, and when you have to run a laboratory test and you want to publish something, then you cover it very wisely. The thing is that our know-how and our expertise is in the pulse compression, thermal wave radar imaging. So also that is a way to get rid of this kind of how to say, uncorrelated noise. Yeah.
Yes, please.
Prego. Well, you know that I'm a coded excitation guy, but I will try with a long pulse, with a step reading and long pulse, very long one. But if I have to do it in the house where there is no damage that can occur, then I will do a long pulse with, for example, a halogen lamp. If I have to do it on a frescoes from a Giotto, for example, then I should be careful about the temperature rise and thermochromism may occur. So depends.
Other questions? Seen.
Pathology of? Okay. Passive, yes. Yes, but they mostly use the hyperspectral camera. Oh, yes. There are some studies. But thing is that if you want to acquire a big volume, then you have to have a very Yes, yes, exactly. There is any? I'm not an expert on food analysis with thermography, more with near infrared lasers. Okay. Using near infrared, not the thermographic. Okay. I really don't know. Sorry.
Okay, other questions? I have a question, is a curiosity, is an interested curiosity, because then you have spoken about the identification of the defects using infrared signal, but I was interested personally, okay, in identifying, for instance, the evolution of damage in a panel. For instance, imagine that you have a problem like this. Typically is my problem. So is a plaster. Inside the plaster, there is a reinforcement, for instance, with FRP. And then we use to strengthen typically such measuring panels with such system. The problem is that when the reinforcement is loaded, then starts to crack inside. So the problem is that from outside, we don't see anything. If we put inside some, for instance, fiber optic sensors, then is something that disturbs the strengthening system. So maybe it would be useful to use something that a system of measure, let's say, or a system of something that can tell us something of interesting on the evolution of the cracks from outside. So if you use, for instance, digital image correlation, we don't see anything because there is the
even
plaster.
with the speckle, you cannot.
No, because yes, we tried, but is an effect.
And what is the? Sorry if I ask you a counter question, but what is the reinforcement made of? It's steel.
Can be steel, can be basalt, can be fibers, glass fibers.
If it's conductive, you can use.
Sometimes it's conductive, sometimes
you can use a selective excitation like eddy current and use the heat from how to say the heat dissipated by the metal itself in the crack from the interruption of the eddy current to get a selective heat on top of the surface, and so you can infer where is the crack. But about the extension, it's a diffusive phenomena, so it spreads.
Yes.
So it's difficult
to quantify.
It's difficult. You need to do calibration at different depths. Of course, it's inhomogeneous, so it's difficult. But there is also another possibilities, which I was trying to do it, but it's too long to explain. There is a way to try to pass from a diffusive phenomena to a propagating phenomena. And so it's called thermal wave, virtual wave, sorry, or Q transform. And so you can extract better quantify the depth of your thing, and also increase the signal to noise ratio, reduce also the thermal diffusion, lateral thermal diffusion. So there are techniques, but for me, I would go to ultrasound.
Yeah. Indeed, this is a technique that is used with all the problems that are related to ultrasounds.
Or acoustic emission.
Acoustic emission, yes, the same, yes.
So I do NDT. Yeah. We do NDT from ultrasound, contact, non-contact water, and thermography, active thermography with eddy currents, and etc. So I'm open for keep going with the discussion. Very interesting.
Thank you for this explanation. Okay, if there are no additional questions, I would like to thank again the speaker for this very, very interesting presentation.
Thank you.
And now there is the coffee break, and then we can then restart with the next webinar.
Just a second, some announcement. Please, for safety reason, the coffee break is outside. So try to save the safety distance and enjoy the coffee break. Thank you very much.
And a very big applause again to the speaker. The speaker is Lucia Figuli, and she will tell us something about measurement of blast wave propagation and evaluation of structural resistance under the blast load. So thank you, Lucia. You can start your tutorial.
Thank you. My presentation is completely different, but I found two words in common, camera and frequency. But I think that will be interesting for you. My name is Lucia Figuli. The name seems to be Italian, but I'm 100% Slovak from University of Žilina in Slovakia. Slovakia is not Slovenia, but we are on the north, and a lot of Italian is changing with Slovenia, so we are a little bit north, near the Poland. I'm from the University of Žilina. I'm very happy to be here because I'm for the first time in Calabria, and my city Žilina is like Cosenza, so it's very nice. We have a university with different faculties. I'm graduated from the Faculty of Civil Engineering, but actually I'm at the Faculty of Security Engineering. And for this reason, my lecture and my research is connected with the security. I'm evaluator of national international research project. I'm part of the NATO Science for Peace and Security Programs Independent Scientific Evaluation Group for the second period, and this is an honor for me because each country has one evaluator and one representative. I had many fellowship and stipends, mainly in Italy, so I'm speaking Italian too. If someone wants to speak in Italian, it's possible. About this tutorial, the aim is to introduce you the accidental loads on the structure, to present experimental open field blast test, methods how to measure the principal characteristic of blast wave and behavior of blast loaded structure. And then the second part is introduce the methodology and something about the structural design of the blast loaded structure. This is one photo. I'm connected, or my research activities are connected with the NATO, and one of Center of Excellence of NATO Explosive Ordnance Disposal is focused on the blast, and each two years is organized NATO EOD demonstration and trials, and we are the unique university presenting the research activities at this event for many years. Recently, we published the book about the explosive. For now, it's only in Slovak, but we are preparing the English version. And why I'm interesting, or why I'm researching in the blast. This topic was forgotten for many years, but now recently with all the terrorist attacks is very popular, and with the war in Ukraine, it's really like needs to be researched. The literature and the research are old, and there are now the researchers are making things, but still it's not researched in profound. The blast and explosion is one of the accidental loads, and we can say that another accidental loads are fire, earthquake, impact, and explosion. All these four loads act differently. And the explosion or blast load is interesting Because it's a dynamic loading, we have to need an explicit calculation. We have a large transformation. The material properties are changing under this type of explosion. And we have ductile materials, the plastic stress occurs, so it's different from another accidental loads. So some basis about the blast wave. The blast wave is creating after explosion when the detonation generates hot gases, which expands in the space. There are two basic form of blast pressure. Depends on the substances. So when we have an explosive, the blast pressure is rapidly growing and then going down under the atmospheric pressure. And with the gas, we have a little bit hill that it's the pressure is going continually and then it's dropping down. So we can recognize two phases. One is positive phase and one is a negative one. Explosion and the blast load is very, very interesting from the point that each can take place in different location, in different climatic condition, and it can be initiated differently, or we can use different explosives. So we obtain different numbers or values of the blast pressure. Everybody knows TNT explosive, but commonly is not used because it's very hard to obtain TNT. There are some explosion like traditional army explosion, TNT, PENT, RDX, which are used in areas of current conflicts, but by terrorists are used homemade explosive. There are two, like this one group, hexamethyl and acetone peroxide, and the major part of homemade explosive is so-called ANFO explosive, is ammonium nitrate and fuel oil. This is the picture from our test. We made we mixed it on homemade explosive, and we made a different test, and there are 3 different variants. We mix it with oil and aluminum powder, and oil with TNT. We made a different field test, so I would like to present you some tests and how we measured the blast wave. We made different weights. For example, this round was made, we had 2.3 kilograms. It was like it had to present the pipe bomb, then 4 kilograms bomb belt and 9 kilogram bomb vest. And we used a different type of ANFO explosive. For the field test, we made different form of explosive, type, shapes, and way. And we was a little bit playing with the explosive. So you can see some pictures from the real field test. We made like different type and form of explosive because terrorists are not using like a really nice shape, but are using, how you can see, they are using a lot of different forms. So we had different charge shapes like block, cylinder, and sphere. Here are some pictures from the field test, and you can see ammonium nitrate used for the ANFO explosive. It's a common filterizer using in agronomy, and you can see like these small prills, which are not explosive. We measured different characteristics like density of explosive, weight of explosive, behavior of the blast wave, and propagation in the time. Maximal pressure. Then we made the different tests, and we had steel beams loaded by the blast wave. So on the steel beams on the structure, we measured acceleration of the structure, stress in structure, and then meteorological data like temperature, pressure, humidity, and velocity of wind. For the measurement of blast pressure, we used a sensor, piezoelectronic sensors in the form of long form. For example, for this test, we placed 4 sensors, and we wanted to obtain like propagation of the blast wave in all directions. These are pictures or photographs from the test where we tested steel structures, and we wanted to obtain deflection. We used for the measurement of deflection, digital deflection gauge, and for acceleration, deltatron accelerometers. Here are some pictures. We had a different round of the test, and the sensor was placed in different position. And now you can see the first results, and you can see in this figure the first phase, like the positive phase of the blast wave, and the second negative phase. It seems to be like the same picture, but there are 2 differences. And here we are from the horror movie. So these are some tests and pictures from the blast resistant steels. And from the camera, you can see the blast wave propagation in different time sequences. So after the test, we can obtain the blast wave. Normally or officially, the blast wave is recognized like positive, specific in its positive phase and negative phase. But from the test, sometimes the results are not so clear. For example, the next picture is the real blast wave time history, and you can see that sometimes you can't obtain one peak, but you have a different peak because like the explosive, it's not both in one moment, but in different sequences. For example, it's in Slovak. There are different blast wave from the different tests that you can see that it's not really like from the book that the blast wave propagation is different. Here are some experimental results, and we wanted to measure like propagation in all direction, and you can see that the propagation of the blast waves, it's not equal in all direction, but it's a little bit changing. Here are some data from the field test that we made the comparison between homemade ANFO explosives and industrially made. So you can see the differences between the explosive, and you can see that industrially made are really efficacy respectively to the homemade. Important is how to set the blast wave and the pressure of the blast wave. Analytical setting is based on the so-called scaling law, and this scaling law saying that during the detonation of 2 charges of the same explosive having the same geometry but different mass and located at the same reduced distance from the point of interest, they generate similar pressure waves as long as they are in the same atmospheric conditions. So this scaling law was made by Hopkinson and Kranz, and like real charge weight and real distance is calculated with the scaled distance, so-called scaled distance, and the maximal pressure is based on the distance from the point, from the structure, or from when we want to protect people. So we have to consider the distance from the object, from the people, and the explosive charge. There are a lot of different relations made by different authors. Basically, they are based on the empirical results. So you can see some different formulas how to set the maximal pressure of the blast wave. Kingery-Boltzmann is primarily using in America, in technical manual, in United Facility Criteria, and International Ammunition Technical Guide. There are different factors who are entering in this estimation. One of this factor is so-called TNT equivalent, who is based on the characterization of the TNT. But as a characteristic express so-called heat of combustion, but the problem is that this value derived from a heat of combustion, but this heat of combustion is theoretical value, and for example, the heat of combustion of Slovak produced DAP with AMPHO explosive is the same as TNT, but the efficacy of these two explosives is very different. So it's not true. So with my colleague, we made other relation for the how to set the maximal blast pressure, and we considered explosive pressure and density of explosive. This is our relationship which can be used for AMPHO explosive, and these are some good results and comparison with the experimental testing. How can we use software for the prediction of blast behavior? There are three approaches how to do it. We have empirical methods, semi-empirical, and numerical methods. From all these methods, we recognize the simplest one is so-called ConWeb, XDAM, or 3D blast, is based on the semi-empirical methods. And for example, a lot of people knows LS-DYNA and ANSYS Autodyn, who can be used for the blast wave propagation. For the modeling of the blast loaded structure, we can use Visual FEA and Abacus. These two softwares based that we have to model the blast load as a function changing in the time, and then with this function load the structure. LS-DYNA and ANSYS Autodyn, we can make the blast wave propagation in the space, and then made the global analysis of the element, and this element is loaded by the blast wave which was modeled in previous step. So you can see some simulation of blast wave propagation. And you can see the reflected wave from the ground. Okay, we made a numerical simulation with ANSYS Autodin, and we made our own software for the calculation of the blast pressure and blast characteristics. And for the structure under the blast, if we want to protect people and want to protect structure, we need to know the blast load and blast wave, and then how is the behavior of the structure under this blast load. So it's impulsive loads, and for example, damping has very little effect on the first peak, so can be neglected, and some damping can be ignoring. There are differences if we have like nuclear bomb and overground bomb, like for terroristic or for the war. If you have a nuclear bomb, the blast pressure is going from the top to the down, and in the distribution in the ground explosion is different. It's like affecting one side and then is going outside. For the blast wave in European Union, we don't have like exact codes and standards. We have Eurocode 1, but there is only 1 page or 2 pages about the blast, and there is written that it can be used for terrorist attacks, so we don't have nothing. We have a military standard STANAG 4440, but is speaking only about the security stance of distance. And in America, they have this Bible of all the blast wave design, and it's unified facilities criteria. If you want to resolve and want to know how the structure is the behavior of the structure, we have to resolve. We can model the structure as so-called single degree of freedom. It means that all the mass we put in one point, and we made oscillate this point. So we have to resolve this differential equation, and we have 3 possibilities how to do it, like how consider the blast effect. One is with the linear decay, and one is exponential decay, and the third one, the hardest and difficult one, is consider the negative phase. You can see like the pressure on the right side. We have to use a different factors to model like more realistic to the structure, to the structure, and these are results of this differential equation. What is important to obtain, like the maximal limitation, which can be the structure can load. This is very simplified methods, but we can use this angle of limited rotation according different materials. How to protect people against the blast? The most economic and the most easy way is to work with the stand of distance, because if the stand of distance, if the distance of the explosion and of the people, of the person, or of the object is higher, the pressure and consequences are lower. It's in the Europe. It's recently adopted methodology is called crime prevention through environmental design, and this methodology is focused on the design of urban spaces and environmental spaces, and how to design the spaces to do it safer for the people and for the structure. We can use different barriers to make the standoff distance, and to use the different detection system and elements how to detect explosion and avoid to enter people with the explosion in the places. The other method how to protect the structure is to use so-called retrofit technique, and this means to use different materials who can behave better under the blast load. Some sandwich materials or polyurethane layers, high street concrete, and there are a lot of researchers. There are a lot of research about to find the new material which can be fit the best for the protection of important buildings. We made some tests and modeling and using like differences using mineral wool, thermal insulation, thermoplastic polyurethane, or high strength mortar. So something we made. So this is all for me. Thank you.
Thank you.
It was completely different, but I think that it was interesting a little bit.
Absolutely. It's very interesting. Any question? Please. Yes, please.
Yeah, you can model it in this way, or generally model it in like the free space, and then you put like structure and you affect the structure from the blast wave who is created in the free space.
There are kind of periodic structure within trees for protecting from earthquakes. Basically, to that small your feet is like premium mass. There is by end the metaphysics, which is the most interesting one today. And you talked about you say the honeycomb, no? Honeycomb we have actually that some fence and then are not allowed to go.
Yes, I think this is possible. There are yes. I don't know if because there are not a lot of studies about these materials using for the blast protection because it was area of the military and it was they had a need to do it like practical for the practical buildings, but in the last years we have critical infrastructure laws that we have to protect the critical infrastructure buildings and critical infrastructure. So something is changing, but I don't know more about this one.
Other questions? Please.
Yeah. The problem is that it's really hard to do this blast test because you need we are very happy to have this possibility because you need like the polygon and the special place who has to be with the sand ground, and you need like the ambulance, you need pyrotechnics, you need a lot of people doing this test. So we was happy to do this one, but I'm open to do and to using it, I think. But the problem is that the blast is very, very big. So we, for example, when we with camera we measured the blast with propagation, we were inside the special bunker, concrete bunker, and I don't know if it can be like it was the protective glass and the concrete wall, so we can't be like directly near the blast phase. So if it's technically possible, why not? Yeah. Yeah. Okay. Okay, for the next time.
Thank you very much, Lucia. Just a quick curiosity from my side. Your opinion, which are the weak points of the measurement system that are used, and your opinion of how they can be improved, maybe? For example, the fact to increase the number of sensors, or for example, to add further kind of sensors to evaluate other aspects. In your opinion, it could be feasible, it could be interested to apply some research in this field?
I think yes, because for now, like USA, the guide for all this research, and they made all this research, and they have standards, and it's usually further. We in Europe, we are like, we have only small things, but it's like every year there are a lot of people, and with the how the terrorist attacks are increasing, and now with the war in Ukraine, so it's sad, but we have to do it for the protection. Yeah.
Thank you very much. Thank you, Lucia.
I have a curiosity, if I can.
Yes.
I have a curiosity because yes, many years ago, yes, I had the opportunity to study some problems of explosions related to the protection of built heritage, mainly dealing with mesostructures, existing mesostructures. And then I was facing a problem that then I would like, if you can, to give me some tips regarding these results, because we tried then to analyze such structures, and as you correctly stated, that is the most important thing for the protection, and we concluded the same thing, is to give a distance between the structure and the point where there is the explosion. But we tried to simulate basically the phenomenon that is indeed very complex, using, as you stated, finite element codes like Abacus, LS-DYNA, fragmentation, and also some approaches that were based on fluid structure interaction, so finite elements plus finite volumes, etc. That is a very complex topic. And what we found that, and is something that probably makes sense, is that the result is very sensitive regarding the typology of analysis that you carry out and the tool that you use. So my question is a curiosity, of course, if you have experience in this regard on the advanced analysis of such kind of tools.
Me personally, no, but I have my colleague from Slovenia, and who's making the research, and he made a lot of numerical analysis. So I can show you the link, and he has a lot, or in contact, make you in contact, because he really made a lot of analysis, and for me and for our research too. But the problem is that this software can analyze and can give you nice videos and nice pictures, but the problem is characterization. With the blast, like there are different chemical substances, and like you need the coefficient who really describe the explosive. And with TNT, it's okay because TNT is like a traditional explosive. We have a lot of characterization. But for example, for homemade explosive, it's completely different because you can mixture it in different ways, and you can obtain like real characterization of the input for the simulation. And there the second one is that when the blast wave is propagated in the free space, it's nice. But in real space, it's not free because you have like the
interaction. Yes, with
interaction with the ground, interaction with another building. So it's really complex, like the problem.
Yeah, thank you. Thank you very much.
Thank you very much. Thank you to all to stay here, to participate to these tutorial days. Thank you to the speakers. Both you have brought very interesting topics, and I think suggestions for our research maybe to work together. And this is one of the aim of this workshop. So thank you again, and we will meet this evening at 7:00 p.m. at the gala dinner at Colosseum, Bar Colosseo, and on the website you will find the addresses. It's near to it. It's near here to here. Thank you very much. Thank you.